limit as x approaches c of f of x equals to L. Okay. That means if we have some function here, so we're looking at what happens to the function as x gets closer and closer to c. So x is zeroing in on c, coming around this way and from this direction. You got to be coming at it from both sides. Just like if you were doing its average velocity, you'd be stopping at a time before, starting at a time before, and then stopping at a time after. Same kind of idea here. Then we're asking the question, what value does the graph approach on the y-axis? What value does that approach on the y-axis? So here's our value L. And so we're looking at what do we approach on the y-axis. What value, if any, does it zero in on? And you can kind of see from the picture here that, yeah, it does zero in on the value L. And so when we say the limit as x approaches c of f of x is equal to L, what this means, so that's the visual picture, means as x gets ever closer to c, then f of x gets closer and closer to L. So when we say the limit of the function is equal to L, that means as we close in on x and get as close as possible, you're going to keep getting closer and closer to L, as close as you want. But the limit is not worried about f of c. He doesn't care what actually happens at c. Limit's only worried about what happens around c. Okay, important thing. Although in many situations, we're going to find that the limit and the function value turn out to agree. And they're going to actually turn out to be the same value. But sometimes, particularly in the situations that we're interested in calculus, the function value isn't going to be defined, but there still is actually a limit value. So that's the kind of little context there for limits. And now let's consider an actual example. Let's consider the limit as x approaches 2 of x squared plus 1. And what we're going to do is use this idea of getting closer and closer to help us work out the actual limit. So to figure out, to make a guess at what the limit actually is. Okay. So what we're going to do is construct a chart of some x values and our function values. And we're going to look at what happens as we get closer and closer to 2. So let's first start with some values smaller than 2. Like 1.9. And then 1.99. Alright, that's even closer. And then 1.999. And then I'm going to put 2 here, and I'm going to put a little dash inside my chart because I'm not worried about what happens at 2. Okay. And then I'm going to continue on the other side. Values that are a little bit bigger than 2. So 2.001, 2.01, and 2.1. The value is a little bit closer and a little bit further away from 2. And then we want to go in and evaluate the function at those different points to see, well, what's it give us? What's it give us? At 1.9, don't you get 4.61? Okay. And at 2.1, you should get 5.41, I believe. Those two I can kind of do in my head, because I know what 19 squared is and what 21 squared are. The other ones, though, you're going to have to kind of help me out. So if you do 1.99 squared plus 1, 4.96. And then 1.999 squared plus 1. 4.996. Okay. Alright, and then the other two, 2.01 and 2.001. Is that the 2.001? 5.004. 5.04. Okay. And again, those may be rounded off a little bit, but we can get the idea of what's happening. So it sure looks like, as we get closer and closer to 2 on both sides, it sure looks like it's closing in around what number?
5.
Yeah. Sure looks like it's closing in around 5. And that's why we look at it from both sides. So we can kind of get a boundary value. Now that doesn't guarantee for us that it's 5, but it gives us a good guess that it's 5. Now in this case, we can actually plug 2 into that equation, and it turns out to be 5. Next week when we come back after our test, we're going to do another example numerically where when we start trying to evaluate it, we can't actually evaluate it, but when we look at its limit, it does look like it's approaching a particular number. Okay, so we'll be looking at that next time. There is no homework yet, so just kind of get ready for the test on Friday, and we'll see you then.